All right, I think it's time. Welcome back, everybody. Um, it's our last week before Thanksgiving. I'm sorry I haven't graded the tests yet. Might do them tonight. It'll be soon at least. My apologies for the delay. Uh, we are more or less going to be back on our regular schedule, although there's no homework assignment due this week because we didn't do enough new stuff last week. So I guess that means we won't have homework due for a while until after the break. So we can all relax a little bit. You can all relax a little bit. It's not much easier for me. All right. I think we're ready to start a new chapter in the book. The next chapter is all about something that you all know and love, the derivative. Can you believe it? We've been talking about continuity and limits for so long. I don't know if you ever thought we would make it this far. The derivative. It's a big deal, everybody knows. And actually, we don't have all that much that's sort of special to say about the derivative. We are not, here's one thing we're not going to do, is like do derivatives over and over again of particular example functions, which is what you typically do in a calculus class. Because once you understand, like our goal is to understand the derivative at a deeper level, and it's not really necessary to work through a million examples just to convince ourselves that we understand the derivative. So stuff, for the most part, will go sort of the way you might expect it to go as far as the derivative is concerned. Anyway, let's just get it started. So we are going to start with a definition, and we're going to use the usual definition of the derivative, like the same definition that you would have seen in a calculus class. So I'm going to say let f be a function and c be a particular real number, where c is in the oh, I got right up to the edge there.
It is.
I'm all right. C is in the domain of f, of course. I want to talk about the derivative of f at c. So then, this is what I'm defining. The derivative of f at c is this. We write it as f prime of c, of course, as always, and it is defined to be the limit. Anybody actually remember this definition?
Isn't it the limit of f of h minus f of x over h?
Something like that. So there's
x plus h.
yeah. So actually, that is a different form that I'm not going to write, but I'll write it over here. This is not what our book uses as the definition, but they say limit as as h approaches 0, f of x plus h minus f of x over h. This is the definition which I most commonly use. Like when I teach calculus, this is what we always use. It is equivalent to this other one that I'm going to write on the left side, and this is the definition that our book uses. Oops. Limit x goes to c, f of x minus f of c divided by x minus c. All right. We're going to use that as the definition. These two things on either side of that bar, they are equivalent to each other, where if you use, instead of c, you use x plus h, you'll get the same thing basically. But this one on the left is what our book uses. It turns out, you know, they're equivalent. Most calculus books use the one on the right, or they often, instead of h, they call it delta x. You get f of x plus delta x minus f of x over delta x. But the one on the left is a little harder to use if you're doing examples over and over again, and like you have to do weird simplifying, which calculus students don't like. For us, it's not really going to matter. And the one on the left is a little more convenient for the kinds of stuff that we're going to do. So this is the definition of the derivative of f at c. It is a limit, all right? So I don't know if you expected me to like immediately start spitting epsilons and deltas or something, which we usually do in this class. All our definitions are based on some weird epsilon stuff. You don't really have to say that for the definition of the derivative. But of course, the epsilons are all like built in right here. So if you really want to sort of get under the hood, then this really is some statement about some kind of epsilon nonsense. But you don't have to say all of that to make the definition in terms of the limit. All right. Let me just say in this case, so I'll say if this limit exists, then we say f is differentiable at c, right? Differentiable means the derivative exists. Okay. This is everybody's favorite, you know, we all know and love the definition of the derivative. Okay, let's just real quick do a particular example. How about f of x equals x to the power n, where n is any number other than -1. You know, if n equals -1, you get the natural log when you take the derivative. Let's show that f prime of x equals, anybody remember? You better remember this. What's the derivative of that? You all remember, but don't want to say it.
N times, oh, sorry. N times x to the n minus 1.
Yes, that's the derivative of x to the power n. All right? This is like every calculus student's best friend, this formula. You do this over and over again in all of your derivative examples. Let's see if we can demonstrate that. So, first of all, the definition as I just wrote it, I never actually said f prime of x. You're talking about the derivative at each individual point. So, would you mind really, this is not incorrect to say f prime of x equals n times x to the n minus 1, but I'm going to say just sort of let c be any real number, and then we'll show that f prime of c equals n times c to the n minus 1, right? We have to do this by computing that limit over there, so we're going to find f prime of c. It is lim x goes to c of f of x minus f of c over x minus c, right? And this is f of x is x to the n, right? I'm just plugging in the function. Lim x goes to c. All right, x to the n minus f of c would be c to the n, because that's what the f is. The f is nth power divided by x minus c. All right. And now, if you want to simplify this limit, you got to do some weird kind of canceling or factoring or something. Here is a weird rule, so I will say, note that this is a true fact. X to the n minus c to the n is equal to x minus c times, I don't know if you know this fact, x to the n minus 1 plus c x to the n minus 2 plus c squared x to the n minus 3, etc. plus finally all the way down to c to the n minus 1. So this is like that formula about the difference of two squares, which everybody knows. You know, a few times ago we used a similar formula about the difference of two cubes, which not as many people know. There's actually a formula for the difference of two nth powers, no matter what the n is, and the formula is this right here. And if you don't believe me, I don't expect that you had this formula memorized or anything, but certainly now that I show it to you, if you don't believe me, you can check this just by multiplying out. You have to distribute everything, and you will notice that everything cancels out except for the first and the last term in the product there. All right. This is you could say this is like related to the binomial theorem. Anyway, what does that give me? So what I had above, f prime of c, like this thing here, I'm going to replace the numerator by all of that. I'm not going to write it down though, because then immediately this guy will cancel the x minus c, right? So if you plug this big thing into the numerator here, and then cancel the x minus c, all that remains is this. So f prime of c equals lim x goes to c of that other stuff, x to the n minus 1 plus c, x to the n minus 2 plus blah, 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 plus c to the n minus 1, right? Can we do anything with this limit? We're getting somewhere, I guess. Any suggestions here?
We can apply c to x.
Yeah, plug c in for x, right? We're trying to take the limit as x goes to c. This, what I'm looking at right now, is just a polynomial, isn't it? And so we should be able to just plug the value in. We already know a polynomial is continuous everywhere. So if you want to find the limit, you can just plug the value in. Why didn't we plug the value in at the very beginning? Well, because we started with this, which has x minus c in the denominator. You cannot plug c equals x, or sorry, x. You plug the number in, which is c. So I'm going to plug c in for x, but you can't do that at the beginning because that will give you 0 in the denominator. But after doing this weird trick, we no longer have a denominator, so that's not a problem anymore. So I'm going to plug in. So here I'm going to plug x equals c, right? If you have x approaching some number, the way you find the limit, if it's continuous, is you plug the number in for x. So here I have x approaching c, so I plug c in for x. What I get is c to the n minus 1 plus c times c to the n minus 2 plus blah, 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 plus c to the n minus 1. What can we do with that? Can we simplify? What do I get from c times c to the n minus 2? Actually, that will be c to the n minus 1 because you add exponents when you multiply. In fact, everything here, even all the things inside the dot, 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 they are all equal to c to the n minus 1, aren't they? Plus c to the n minus 1 plus c to the n minus 1. If you look here, you will notice if I were to replace x's by c's, then the exponents, they would all be c's, and the exponents would add up to n minus 1 every time. Like so. And what is that? Well, we can, it's just c to the n minus 1 added together a bunch of times. How many times? Well, if you look at this here and think about it, you will decide there are n things here being added together. So this is actually equal to n c to the n minus 1. And that's what we wanted to show, isn't it? F prime of c is, can't see my exponent there. Right there. N c to the n minus 1. Right. Any thoughts about that? This is the rule from calculus. The power rule, they call it. The power rule. Everybody loves the power rule. All right. Excellent. Let's try. I actually do want to talk about some other examples, although they're going to be weirder examples. Examples like this one is not a weird example. You talk about this in a calculus class all the time. I want to talk about some weirder examples, though. Let's look at. So I want to say some functions, even some continuous functions, are not differentiable. And I would like to do an example like that. I think actually maybe you can guess what example I'm thinking of. Anybody, what's your favorite example of a continuous function that is not differentiable? I have basically one idea in mind. If somebody approached me on the street and asked me to give them a continuous function that's not differentiable, really only one thing.
Is it the absolute value?
Yeah, the absolute value would come to mind, right? The reason it's continuous but not differentiable, it's not differentiable right at 0 because of that pointy point. There's no... I didn't say this, but we all know the derivative represents the slope, right? And the slope, as such, doesn't really exist at that point because there is no unique tangent line which gives you the slope at that point. Even though this is continuous, I hope you agree, the function really does approach that point, and there's nothing wrong with that function in terms of continuity. But it is not differentiable. So let's see if we can demonstrate that. So let's show. So here, f of x is absolute value x is not differentiable at c equals 0, right? Right at that pointy point. Actually, it is differentiable everywhere else, but not at that point. All right. Everywhere else, the derivative is always plus 1 or minus 1. But at that point right there, there is no derivative. All right. This will involve showing that some limit does not exist, and that always involves sequences. That's how we show that a limit does not exist technically. So here's one thing that you never did in a calculus class probably. To show that a function is not differentiable by showing some limit does not exist. So the derivative, if it did exist, which it doesn't, f prime of 0 would be, in this case, lim x goes to 0, f of x minus f of 0 divided by x minus 0, right? I'm using the definition of the derivative. It's lim x goes to c, f of x minus f of c over x minus c, using 0 for c. All right. What can we do with this? I want to try and simplify this as much as I can. F of x, I can just write absolute value x. What is f of 0 in this case? It is 0, yeah, it would be the absolute value of 0, which is 0. So, I mean, I guess I'll write it. On the bottom, x minus 0. But these zeros, you don't have to write them, right? So this is lim x goes to 0, absolute value x over x. And this is the point at which we need to demonstrate that that limit does not exist. So this can't be simplified anymore. This limit does not exist. And how do we do that? We do this using sequences. And I think in this case, the easiest way would be to find two sequences of x's which approach 0, but their values, when you plug them into this thing, go to different answers. You get different answers when you plug them into that. What you should be trying to imagine in terms of these sequences is two different, 0 is a point where it's not continuous. Can you imagine two different sequences which approach 0? Where you're not really looking at the values along the curve here, but you're thinking about the slopes as you approach 0. Their slopes do not approach the same value. Here, I'll get it started. How about I want two sequences. Which both approach 0, but absolute value x divided by x approaches two different values, right? How about one can be 1 over n? That's my favorite sequence that approaches 0. Anybody got an idea for a different one?
Minus 1 over n?
Yeah, how about negative 1 over n? Because on the picture, I hope you are thinking about if I approach from the right side, the slopes will always be plus 1, right? But if I approach from the left side, the slopes will always be negative 1. So that's the idea here. So xn is 1 over n. I'll call yn is minus 1 over n. And they both indeed do approach 0, which is what we want. But their values, when you plug them into the function, now not the function f, but the derivative function, which is this absolute value x over x. So I'm going to look at absolute value xn over xn, and separately absolute value yn over yn, right? I'm plugging each of those two sequences in, and hopefully they have two different values. They converge to two different values. What does this one look like? It is absolute value 1 over n over 1 over n, but absolute value 1 over n is 1 over n over 1 over n, and this is 1. Now this is a sequence where all the terms equal 1, and this of course converges to 1 because because 1 as a sequence, right? These really are sequences. Is a constant sequence, 1, comma 1, comma 1, right, forever. What happens when you do this one? Yn over yn. Yn absolute value over yn. I get the sequence absolute value negative 1 over n over negative 1 over n. Take the absolute value up top, you get 1 over n over negative 1 over n. And this is negative 1 every time, which of course converges to negative 1. What am I doing here? Negative 1. All right. And the fact that these are different means that the limit does not exist. So lim x goes to 0, absolute value x over x does not exist. All right. And so that means f prime of 0 in this example does not exist. Any questions about that one? This is how you show something is not differentiable. You typically use sequences because it amounts to showing that some limit does not exist. And in almost all situations, the best way to show that a limit does not exist is using sequences. All right. Great. That was a simple one. I thought I have two sort of stranger examples. It's maybe just one example and a variation on that, on the one example. Everybody's favorite sort of weird example, maybe not your favorite, among the favorites of a weird example. I would like to know, what about one of my favorite functions, f of x equals x, sorry, really, I mean this, x sine 1 over x. Remember this guy? Or 0? If x is non-zero, the formula is x sine of 1 over x, and then 0 if x is 0. So what this looks like on a graph is, remember this is the one that it sort of has asymptotes like that, kind of, and then the graph of it does this. My kid likes the looks of this one. And because I said that second, the two pieces, 0 on the second one means there really is a value right in the middle at the origin, all right? If you didn't say this part of the definition, then this function is not defined at x equals 0 because you can't do 1 over 0 right here. So you gotta sort of plug the hole by putting that in, all right? My question is this differentiable? All right, that's what I want to know. It is continuous, right? We've shown that this one really is continuous even at the origin. You know, at the origin is the only place where anything weird is going on. So really, more specifically, I would like to know, is f of x differentiable at the origin, x equals 0, right? It is differentiable at all the other points because otherwise it's more or less an ordinary line. It only gets really crazy near 0, right? I don't know if you have any thoughts about this. Does anybody have a feeling? If we were all in class, I would ask you to give me the thumbs. Yes, it is differentiable. No, it's not differentiable. What do you think? How about this? Can you give me a thumb in the Zoom? This will be fun. I've never done the thumbs. Can't you do thumbs? Or you can do yes, no, can't you? There's like a button in the, I can see the buttons in the participants list. Somebody gave me thumbs. Differentiable or not. You want to imagine if you were to zoom in on this point, right? The derivative, the slopes. Do the slopes actually approach anything? Or do they just go crazy as you approach the origin? That's what I want to know. Get your votes in. I don't really, you don't have to be able to prove it. I just want to, I wonder. You know, when I think about this, like I know what the answer is, but when I think about this without going through the computation, to me it's not clear. What I mean, maybe the derivative is 0 because it does seem like the function kind of flattens out. but at the same time, it also seems like the function is going up and down like crazy, which means the slopes are basically alternating between positive and negative, like over and over again. The slope is going extremely positive and negative. All right, I see some people figured out how to do the thumbs. I got 2 thumbs up and 4 thumbs down. So I guess of those 6 people, most of you thought it was not differentiable. Let's work it out. Actually, it is not differentiable at the origin. Let's see if we can work this out. Is f of x differentiable at the origin? The answer will be no. Let's just see if we can do it. We're going to use the definition of the derivative. So f prime of x, well, really what I care about is f prime of 0, right? At all the other points, it doesn't really matter. I mean, all the other points, it is differentiable because the other points are fairly ordinary. It's really just 0 where the insanity happens. We use the definition of the derivative. I go lim x goes to 0, f of x minus f of 0 divided by x minus 0, right? F of x. Now, inside this limit as x goes to 0, remember, when you take the limit, you're really looking at all values other than 0, all of the nearby values. So when I plug into this limit here, I can use the formula that you see right here. All right? When I plug in for f of x, I'm going to use this one. Now you might say, well, that's not really f of x is not really that. F of x is this both pieces. But when I'm taking the limit, I only consider nearby points, not actually that point specifically. So here I'm going to use x sine 1 over x. And then minus, what is f of 0? This you can look at the definition.
0.
It is 0. Yeah, that's what this special thing here means, right? If x is 0, then f of 0 is 0. So I go 0 here, and then divided by x. Minus 0 is x, right? What can we do with that? Actually, this simplifies quite nicely. You might have wondered, am I going to have to do some weird random trick with the sign of something or other? The answer is no, you don't have to do any weird random trick. In here, of course, I don't need to write minus 0, and then these x's will cancel in the fraction. This x here and here, right? And so all we end up with is lim x goes to 0, sine of 1 over x, all right? But this limit does not exist. Actually, we've discussed this one before. This does not exist. If you recall, sine of 1 over x, its graph looks like this. It's the same kind of thing, only its values are always between 1 and minus 1. But anyway, the limit as x goes to 0 of that does not exist because as you approach 0, the y values do not get close to any particular number. They continue to oscillate between negative 1 and 1. All right. So the moral of the story is f prime, well, can I just say f is not differentiable at x equals 0. All right. And the way I would try to explain that is like this right here, if you think about it, this right here represents the derivative of this function. At least near 0, the slopes of this original function, they look like this. And so these they oscillate between 0 and minus 1 and 1. And they do not approach any particular value, the slopes. All right. That is an interesting example. I got one variation on this, which I think, I don't know if that result surprised you, that one was not differentiable. This one is a bit of a surprise, though. X squared sine of 1 over x. This one, I'm here to tell you, is differentiable. Even though the graph looks very similar. Is differentiable at x equals 0. So the graph of this one, the other one, x sine 1 over x, it has this weird oscillation, but it sort of has these kind of boundary lines or something at the lines y equals x and y equals minus x. This other one is similar, only these sort of boundaries that it has are at y equals x squared or minus x squared. And so this one, the graph looks like this. All right. And sorry, I meant to, sorry to squeeze this in. I meant you got to plug the hole in, right? In the same way. So this, if x is non-zero, sorry about that. And 0, so it does have this value in the middle. All right. For some reason, that x squared, this is the only difference, is this x squared here, right? If you use the squared there, this one is differentiable, where the other one was not. Even though the graphs, they look very similar to me, this one maybe is a little pinchier near the middle there. The curves on either side are getting funneled into this parabola shape rather than a straight line shape. Does that really make a difference? Yeah, actually, it does really make a difference. Very strange, but strange but true. Let's see if we can we just work out the details? It's a very similar kind of playing around with the limit as what we did before. I'm going to try and do the same thing. So this time around, I get f prime of 0 is lim x goes to 0, f of x minus f of 0 over x minus 0, right? Same idea. The only difference is I got an x squared instead of a x. So this is lim x goes to 0. X squared sine 1 over x minus 0 divided by x minus 0. Again, these zeros don't matter, and these x's can cancel one of the x's. So I end up with lim x goes to 0 of x sine 1 over x. And this limit actually does equal 0, right? Remember, the graph of x sine 1 over x is this one with the straight line boundary is this, right? And as x goes to 0, the function value goes to 0. So the limit of that really is 0. So in this example, so for this function with the square in it, f prime of 0 actually equals 0. Right? Very weird. The difference between this picture here and this picture here, this one is not differentiable at the origin, but this one is differentiable at the origin, and its derivative is 0. Strange but true. Any thoughts about that? One of you still has your thumbs down. You dislike this whole thing. That's all right. You don't have to like it. All right. Hey, now it's a thumbs up. All right, great. I kind of like this. I like the weird examples, as you know. That's just my personality, I guess. I'm here for it. Here's something. Can I just say one more thing? I'm here for the tea. Just put the something. This function, which we just said this function is differentiable, right? We can actually compute the derivative if you use things like the product rule and the chain rule. Can we do that? I mean, we all know the product rule and the chain rule, right? If I have, like, let's just think of the first piece, x squared sine 1 over x, right? Using the old rules from calculus, which we are going to talk about, probably not today, but we'll talk about them next time. The product rule, the chain rule, the quotient rule, right? Here, we can just do those rules if you'll take my word for it that they are true. The product rule here, I go the first thing like it is times the derivative of the second thing, and there I have to use the chain rule. So the sine becomes a cosine 1 over x times the derivative of 1 over x would be minus 1 over x squared. And then I go plus the second part times the derivative of the first part. That would be sine of 1 over x times 2x, right? And we could simplify a little bit. I have x squared on the front. This is going to be negative cosine 1 over x plus 2x sine 1 over x, right? This is the derivative of that. I just did I hope I did that right, the product rule and the chain rule. I hope some of you are like, oh yeah, this is what I've been wanting to do all semester long. Well, this is your moment. If you like the product rule and the chain rule, that was it. This is, of course, this formula works when x is not 0, but the derivative is 0 when x equals 0. We just demonstrated that, right? That f prime, we just proved that f prime of 0 equals 0. So that's what the derivative is of this function. The strange thing about this is if you graph this formula, this part, you have two things added together, right? This part sort of goes to 0 near the origin because of this x here, but this part does not go to 0 near the origin. And in fact, if you graph that, you can do this on your calculator, you will see it's one of these weird things again, but the craziness does not like funnel down in the y-axis. It's caused by this cosine part. This cosine of 1 over x will oscillate between -1 and 1, and it does not go to 0. But even so, we still have, in this derivative, this value is plugged in, f of 0 equals 0. So this is a very strange function in that as it approaches the origin, as you approach 0, the values oscillate like crazy up and down. But once you hit the origin, it just stays put at 0. Very weird. Near this point, they go crazy, but right at this point, the derivative is just 0. Very, very strange. One thing that is true of this then, so here, f prime is not continuous. It's because as you approach 0, oops, it's because as you approach 0 here, the values are going crazy, and they have no limit. Even though there is a value at the origin, but this value is not equal to the limit of the curve as it approaches, because the curve has no limit as it approaches there. So this is an example. Actually, it's kind of hard to find examples of this type. This may be one of the simplest ones. So here, just for emphasis here, f is continuous. F prime exists. So can I just say f is differentiable, right? But f prime is not continuous. I don't know if you ever thought about, is that even possible? It is possible to have a function which is continuous everywhere and differentiable, but its derivative is not continuous. This is an example of that. Very weird kind of thing. All right. Any thoughts about this? This is all I'm going to say about these weird examples. I kind of like these. As you know, I already said that. I don't have to keep saying it. All right. Great. Let's talk. We got 10 minutes left. I want to talk about one simple theorem about derivatives and continuity. So we all know, like the absolute value, for example, it is continuous, but it's not differentiable. One natural question to ask is it possible to be differentiable but not continuous? That would be the other way around. And the answer is no, that's not possible. You cannot be differentiable but not continuous. So this is a theorem. Maybe you talked about this in your calculus class. I don't know. It just says if f is differentiable at C, then f is continuous at C. I said maybe you talk about this in your calculus class because actually you don't need to use the epsilons to do this proof. You can do the whole proof just writing things about limits. So let's see if we can do it. You assume that, I think actually this has appeared on the comprehensive exam, your job to prove this. I think I've seen that before. Not in the recent couple years, but you never know. We are going to assume that f is differentiable. So we're going to assume that this limit, x goes to c, f of x minus f of c over x minus c exists, right? And then I want to show that f is continuous. I think the typical way that we would demonstrate that is like this, right? Lim x goes to c, f of x equals f of c, right? This is what it means to be continuous at c. So the idea is you got to somehow start with this and do some magic on this to end up with that. All right. Unfortunately, this is only one side. There's no equal sign here, so it's not just a matter of doing algebra to rearrange that, but it ends up working pretty easily if you know the trick. So the trick is this. I'm going to begin by doing lim x goes to c, f of x minus f of c, and I'm going to try to show that that is 0, because that would be the same as, you know, this here, what I want to show. And how do we show this is 0? This is, here's the trick, this is equal to lim x goes to c of this thing over x minus c times x minus c. So this is one of the old tricks about I divide and multiply by the same thing. Divide by x minus c, at the same time multiply by x minus c. But now I can use my old, so this is all like this. All of this is inside the limit. But I can use the old rules about limits, right? Each of those two things being multiplied here, each of them, the limit exists. The first one, the limit is the derivative, which I assumed it does exist. And the second one, the limit is actually 0, right? It would be when you plug the limit in, you get c minus c, which is 0. So this I can split apart as two limits. Lim x goes to c, f of x minus f of c over x minus c, times lim x goes to c, x minus c. And like I said, the second part here is just 0, and the first part is f prime of c, right? Times 0. But anyway, this is 0, all right? So all throughout here, what we said, lim x goes to c, f of x minus f of c equals 0. And you can just add f of c on both sides there. So lim x goes to c, f of x equals f of c, right? You might worry about, can I like bust this out of the limit? Yeah, I mean this f of c is just a constant, right, inside this limit. So you can move it to the other side without worrying about the limit. All right, and this is what I wanted to show, right? This means that f is continuous at c. So simple tricks and nonsense here, right? There's not really a big idea to this proof. There's just some playing around with the limits. The fact is, if you already assume that this exists, this limit, it automatically means that the numerator has to be 0. That's the idea here. All right. Any questions about that one? All right, I want to begin next time with our rules for the derivative. Maybe I'll write them down. I'm going to write down the same 4 rules that we always write for limits, just they have a special form when you do derivatives. So I'll write this as a theorem. We don't need to do the proofs of these, although I want to do one of them next time. But this is about differentiable functions, and if you add them together, what happens? If you multiply by a constant or something like that, what happens? This is just like the rules, the algebraic rules for limits of sequences or for limits of functions. You get similar rules about derivatives. So I'm going to say let f and g be differentiable at a point, differentiable at c. And then there's 4 of them. The first one is, oh, I should say then. The first one is f. What? When I add them and then take the derivative, I get the same thing as if I take each derivative and add them. All right. So the left side means if I add the 2 functions together first and then take the derivative of the sum of the 2 functions. And then the right side means you add together each of the 2 derivatives. This rule also you use all the time in a calculus class, so often that you forget that it's even a rule. But this is just a rule that says when you have a bunch of stuff added together, you take the derivative of each of the stuffs and you add together all the answers. All right. The second is about multiplying by a constant. It says if I multiply a function by a constant and then take the derivative, it's the same as a constant times the derivative of the original function. All right. These rules you will recognize from the same rules about limits. Okay, number 3 is about multiplication. Now, this one is a little tricky because the rule for limits is just if you have two things multiplied and you take the limit, the answer is the limit of the first one times the limit of the second one. Not so for the derivative. Everybody knows this. You do not just get f prime times g prime. You get the product rule. So it is f of c g prime of c plus f prime of c g of c. So this one, this is the one that I want to talk about next time in more detail because it's not an obvious answer here. The other ones should seem pretty clear to you, but the third one, I mean, why do you get that weird formula? It's not so weird, but, and you know, I'm sure you're all used to it by now, but it is worth talking about. So we'll discuss that next time. And then there's also the last one is the quotient. And as you know, there's a special rule for that. It is, the way I always remember this is ho-de-hi minus hi-de-ho over ho-ho. That's how I say this in my head. The bottom times the derivative of the top minus the top, sorry, no prime there, times derivative of the bottom divided by the bottom squared. Right? That is the famous quotient rule. All right. And we also, so what I want to talk about next time is this one, the product rule. Whatever we say about the product rule, you can do the same sorts of things and you get the quotient rule. So we don't really need to talk about both of them. And then, of course, we also are going to talk about the chain rule, which is a bit more interesting, a bit deeper, actually, this chain rule than these other ones. All right. But I think we'll leave it at that for now, if that's all right. So I hope you all have a nice evening, and I'll see you tomorrow.